For decades, the most powerful force on Wall Street has not been any individual trader, any hedge fund manager, or any billionaire investor. It has been mathematics. Specifically, it has been the classical algorithms running on classical computers, Monte Carlo simulations, Black-Scholes models, risk matrices, derivative pricing engines, all of them built on the fundamental assumption that computation happens one step at a time. That assumption is about to be broken. And the institution leading the charge to break it is the largest bank in the United States, JPMorgan Chase. What they have done in the past 2 years is not a publicity stunt, not a press release, and not a theoretical paper written to impress academics. It is a series of experiments that produced real, verified, mathematically documented results that classical computers cannot replicate. And when you understand exactly what those results mean, you will understand why every financial institution on the planet is watching what JP Morgan is doing with both fascination and fear. To understand what JP Morgan proved, you first need to understand what quantum computing actually is and why it represents something fundamentally different from every computing advance that came before it. Classical computers, no matter how fast they get, work with bits. A bit is a 1 or a 0. Every operation your computer performs, whether it is sending an email, streaming a video, or running a $1 trillion risk model, is ultimately just a sequence of ones and zeros processed in a specific order. Quantum computers work with qubits. A qubit can be a 1, a 0, or a superposition of both states simultaneously. And when you bring multiple qubits together and entangle them, something extraordinary happens. The computational power does not grow linearly the way it does when you add more classical processors. It grows exponentially. Every additional qubit you add to a quantum system doubles the computational space it can explore simultaneously. This means that a quantum computer solving a problem with 50 qubits is not doing 50 times more work than a classical computer. It is doing 2 to the power of 50, more than a quadrillion, parallel computations at once. That is not faster. That is a different kind of thinking. For most of computing history, quantum computers existed primarily as theoretical constructs, and then as fragile laboratory demonstrations, on machines with only a handful of qubits. The dream was real, but the hardware wasn't. The qubits were too noisy, too error-prone, and too difficult to maintain in the quantum states necessary to perform useful calculations. Every error made the results unreliable, and unreliable results in a laboratory are interesting. Unreliable results in a trading algorithm that manages hundreds of billions of dollars are catastrophic. This is why, for years, the relationship between Wall Street and quantum computing was characterized by cautious optimism mixed with quiet skepticism. The technology seemed perpetually 5 to 10 years away from relevance, until JP Morgan decided to stop waiting. JP Morgan Chase assembled a team of more than 50 physicists, mathematicians, and computer scientists through its Global Technology Applied Research Division. Not 50 software engineers, not 50 data scientists with Python experience. 50 experts whose primary credentials are in quantum mechanics, number theory, and algorithm design. This team has been working for years on a specific question. Can quantum computers perform financial calculations that are genuinely beyond what the best classical systems can do? Not eventually. Now. With the hardware that exists today, like or subscribe right now, because what this team found is something that should be on the front page of every financial publication on Earth. The most significant result came in a landmark experiment published in the journal Nature in March 2025. JP Morgan, working in partnership with Quantinuum, Argonne National Laboratory, Oak Ridge National Laboratory, and the University of Texas at Austin, performed a task on a 56-qubit quantum computer that is physically impossible for any classical computer to verify or replicate. The task was called certified randomness. Here is why it matters more than it might sound. Random numbers are the foundation of modern cryptography and financial security. Every encryption system, every secure transaction, every risk simulation that relies on statistical sampling depends on random numbers. But here's the problem. The random numbers generated by classical computers are not actually random. They are produced by deterministic algorithms, complex mathematical formulas that generate sequences of numbers that look random but are in principle predictable to anyone who knows the formula. In cryptography, predictability is catastrophe. In financial, simulations. It introduces systematic biases that can distort risk models in ways that are extremely difficult to detect. What JP Morgan and Quantinuum produced using Quantinuum's H201 trapped ion quantum processor was genuinely, certifiably, mathematically, provably random. Not random looking, not statistically random. Random in a sense that can be verified through classical computation after the fact, but cannot be replicated or predicted using any classical method before the fact. The quantum Computer generated the random numbers by exploiting quantum mechanical properties, specifically the inherent unpredictability of quantum superposition that have no classical equivalent. Then the team used supercomputers at two of the United States Department of Energy's national laboratories to mathematically certify that the randomness was genuine, meaning they proved with mathematical rigor that no classical computer could have generated the same output. Marco Pistoia, who leads JPMorgan's global technology applied research team, described it as demonstrating a solution to a real-world challenge using a quantum computer that is beyond the capabilities of classical supercomputers today. That is not a marketing statement. That is a precise technical description of what the experiment showed. Like or subscribe, because this single result from JPMorgan has redrawn the line between what quantum computing is and what it can actually do. Scott Aronson, the Schlumberger Centennial Chair of Computer Science at the University of Texas at Austin, and to one of the world's foremost experts on quantum complexity theory, who originally proposed the theoretical protocol for certified randomness in 2018, said he was thrilled to see it realized. Aronson noted that this is a first step toward using quantum computers to generate certified random bits for actual cryptographic applications. When the person who wrote the theory says the experiment worked, the experiment worked. But certified randomness is only the beginning of what JPMorgan is building toward. The deeper financial application, the one that could genuinely reshape the competitive landscape of global finance, is quantum accelerated Monte Carlo simulation. To understand why this matters, you need to understand what Monte Carlo simulation is and why every major financial institution in the world depends on it. Monte Carlo simulation is a method for pricing complex financial instruments and assessing risk by running thousands or millions of scenarios and averaging the results. If you want to price a complex derivative, an option in a structured product, a credit default swap, you cannot use a simple formula because the payoff depends on a path that the underlying asset takes through time, and that path is affected by countless variables interacting in nonlinear ways. So you simulate it. You run a million possible price paths. You calculate the payoff for each one. You average them. That averages your price. The problem is that to get an accurate answer, you need an enormous number of samples. The error in a classical Monte Carlo simulation shrinks with the square root of the number of samples. To cut the error in half, you need to quadruple the number of simulations. To get one more decimal place of accuracy, you need to multiply your computation by 100. This is why pricing complex derivatives accurately is so computationally expensive that banks spend hundreds of millions of dollars every year on the classical computing infrastructure required to run these models. Quantum computing attacks this problem with an algorithm called quantum amplitude estimation. Instead of the error scaling as 1 over the square root of the number of samples, quantum amplitude estimation scales as 1 over the number of quantum operations. This means the error decreases linearly rather than as a square root. In practical terms, where a classical Monte Carlo simulation needs 1 million samples to achieve a given level of accuracy, the quantum equivalent needs roughly 1,000. That is not a modest improvement. That is a 1,000 times reduction in computational cost for the same accuracy. JPMorgan's own researchers demonstrated this specifically for European call options, where the quantum approach required 100 times fewer operations than classical Monte Carlo to achieve the same basis point accuracy. And the theoretical speedup gets larger as the required accuracy increases. For the most complex and most accurate risk models, the quantum advantage is not a factor of 10 or a factor of 100. It is potentially many orders of magnitude. Alongside Monte Carlo acceleration, JPMorgan has produced research on quantum algorithms for portfolio optimization. The problem of choosing the best combination of assets, given a set of constraints on risk, return, liquidity, and regulatory capital. Portfolio optimization is a problem that classical computers handle using approximation algorithms, because the true optimal solution across hundreds or thousands of assets with complex constraint structures is computationally intractable for classical machines at production scale. A February 2026 study testing a quantum approach on real equity portfolio problems found that the quantum algorithm achieved a Sharpe ratio of 1.81 compared to 1.31 for the best classical alternative. A difference that, if it holds up at production scale and across different market conditions, would be worth billions of dollars in additional returns for any institution that can deploy it. These are early results. They are not yet running live on production trading systems, but they are the clearest signal yet that the theoretical speedup from quantum portfolio optimization is beginning to translate into real, measurable performance differences. The contrast between JPMorgan and Goldman Sachs on this question is one of the most revealing stories in all of finance right now, and it has received almost no mainstream attention. About 3 years ago, Goldman Sachs looked like the leader in Whale Street's quantum race. Goldman had assembled its own team of specialized scientists and partnered with Amazon to study how quantum computing could improve returns for high net worth clients. Their internal research reached a conclusion that shocked the people who conducted it. Goldman's scientists found that to solve the specific quantum algorithm they were studying, they would need at least 8 million logical qubits. Qubits that are fully error-corrected and stable enough for reliable. Millions of years of compute time on current hardware. Goldman scaled back its quantum program entirely. The technology, they concluded, was nowhere near practical for investment applications on any relevant timescale. JPMorgan looked at the same landscape and reached a completely different conclusion. Where Goldman saw an insurmountable gap between current hardware and practical application, JPMorgan saw a specific set of near-term problems where today's quantum hardware, operated correctly, already delivers results that classical computers cannot match. The certified randomness experiment is the clearest proof of that. It used 56 qubits, far below Goldman's threshold of 8 million, and produced a result that no classical machine can replicate. The difference between the two institutions is not a difference in technical knowledge. It is a difference in strategy and in how they define the question. Goldman asked whether quantum computers can beat classical computers at Goldman's existing use cases at production scale today. The answer is clearly no. JPMorgan asked whether quantum computers can do anything useful that classical computers genuinely cannot do at all. The answer to that question, as their Nature paper proves, is yes. This distinction matters enormously for what happens over the next decade, because the financial advantage of quantum computing is not going to arrive all at once. It is going to arrive problem by problem, use case by use case, as quantum hardware slowly crosses the thresholds needed to run more and more complex financial algorithms reliably. The institutions that have teams in place, algorithms developed, partnerships established, and workflows tested will be in a completely different position from the institutions that decided the technology was too far away and kept their talent on the sidelines. JPMorgan has been building this infrastructure for years. They worked with QC Ware on quantum deep hedging, a more sophisticated approach to risk mitigation that uses quantum neural networks to price derivatives more accurately than classical models. They partnered with Amazon on quantum algorithms for portfolio construction. They have run experiments on trapped ion, which secures the majority of financial transactions on the internet, works by exploiting the fact that multiplying two large prime numbers together is easy, but factoring the result back into its components is computationally infeasible for classical computers. Shor's algorithm, a quantum algorithm discovered in 1994, can factor large numbers exponentially faster than any classical method. With sufficient qubits and sufficient error correction, Shor's algorithm breaks RSA encryption completely. In 2019, researchers estimated that breaking RSA 2048 would require approximately 20 million physical qubits. A 2025 updated calculation reduced that estimate to under 1 million qubits. And a 2026 paper, using new error correction approaches, suggested the number could be as low as 100,000 qubits under optimal conditions. Current quantum computers have fewer than 1,000 qubits, but the direction of travel is unmistakable. The qubits are coming. The error correction is improving. And every digital signature, every encrypted wire transfer, every SWIFT message, every securities transaction currently secured by RSA or elliptic curve cryptography will eventually be vulnerable. The threat has a particularly alarming near-term dimension called harvest now, decrypt later. Nation-state adversaries and sophisticated criminal organizations do not need to wait until quantum computers are powerful enough to break today's encryption. They can intercept and store today's encrypted financial data right now, then decrypt it later when quantum hardware is sufficiently capable. Financial data from today, transaction records, position information, proprietary trading strategies, could be decrypted years or decades in the future by a quantum computer that does not yet exist. This is why banks, including JPMorgan and HSBC, are already running parallel programs on post-quantum cryptography, working to migrate their encryption systems to algorithms that are resistant to quantum attacks before the threat becomes active. The National Institute of Standards and Technology in the United States finalized its first post-quantum cryptographic standards in 2024, giving financial institutions the approved algorithms they need to begin the migration. But migration at the scale of a major global bank, thousands of systems, billions of transactions, decades of legacy infrastructure, is not something that happens quickly. Every day a financial institution delays. Starting this migration is another day of exposure that harvest now, decrypt later attacks can exploit. McKinsey estimated in June 2025 that the potential economic value of quantum computing in finance could reach between dollars by 2035. That estimate encompasses the performance gains from faster pricing, better portfolio optimization, improved fraud detection through quantum machine learning, and the costs avoided by successfully defending against quantum cryptographic attacks. $600 billion. Concentrated in an industry already defined by razor-thin competitive edges and enormous computational resources. To PUT that in perspective, the entire annual revenue of JPMorgan Chase, the largest bank in the United States, is approximately $200 billion. The value that quantum computing could unlock in finance over the next decade exceeds JPMorgan's entire annual revenue by a factor of 3. The stakes are that large. Barclays piloted quantum credit risk models in 2025 and reportedly achieved approximately 25% better accuracy compared to classical analytics. HSBC is active in both quantum computing through the IBM Quantum Network and post-quantum cryptography. Over 15 global banks, including BBVA, BNP Paribas, Standard Chartered, Wells Fargo, and several Japanese banks, including Mizuho and MUFG, all maintain active quantum programs. Quantinuum announced a $1 billion 10-year joint venture with Qatar specifically to build quantum risk engines for Gulf financial institutions. The quantum computing market itself, valued at roughly $1.3 billion in 2024, is projected to reach $20.2 billion by 2030, a compound annual growth rate of over 40%. The quantum computing stocks reflected the momentum. D-Wave Quantum surged over 2,600% between late 2024 and September 2025. IonQ surged 700%. Rigetti reached all-time highs, with shares jumping over 5,700% in 12 months. And yet the honest answer about where quantum computing for finance actually stands today is more nuanced than any of those numbers suggests. No bank has deployed a production quantum algorithm for live trading or live risk management. Every result JPMorgan has published, the certified randomness, the option pricing speedup, the portfolio optimization research, has been demonstrated on carefully structured experimental problems, not on the full complexity of real production financial data at scale. Goldman Sachs' decision to scale back is not irrational. The gap between what quantum computers can do today and what they would need to do to run inside a live trading system at a major bank is still enormous. The current generation of hardware is what researchers call the noisy intermediate scale quantum era. Devices powerful enough to demonstrate quantum advantage on specific tasks, but not yet reliable enough to replace classical infrastructure for mission-critical operations. The honest version of JPMorgan's story is not that quantum computers are already beating Wall Street's best algorithms across the board. It is that, for the first time in the history of this technology, JPMorgan has found specific, practical problems where quantum hardware has already crossed the threshold of classical capability. That threshold crossing is the news. Because once a technology begins crossing thresholds, the pace of threshold crossings tends to accelerate. The institutions that are already standing on the other side of that first threshold are the ones who will be ready when the second, third, and fourth thresholds arrive. JPMorgan is standing there. Most of their competitors are not. The deeper story beneath all of this is about the nature of competitive advantage in a world where computation determines everything. For the past 3 decades, the financial institutions that outperformed their peers did so in large part by building better classical computing infrastructure, hiring better quantitative analysts, and running better classical algorithms faster than their competitors. The edge was always about doing the same kind of computation better. Quantum computing changes the fundamental premise. It does not offer a faster way to do what classical computers already do. It offers a completely different computational paradigm that can solve entire categories of problems that are not just slow for classical computers, but are in principle impossible. Certified randomness is one such category. Certain portfolio optimization problems are another. The cryptographic threat is a third. In each case, the line between quantum and classical is not a line of degree. It is a line of kind. When JPMorgan's head of quantum research stood before the results of the Nature paper and said his team had demonstrated a solution to a real-world problem that is beyond the capabilities of classical supercomputers today, he was not saying JPMorgan is now running quantum trading desks. He was saying something subtler and more important. The era of quantum computing being purely theoretical for finance is over. A line has been crossed, and the financial institution that crossed it first, that invested the team, the time, the partnerships, and the intellectual capital to be the one standing at the frontier when the first threshold fell, is the largest bank in America. The race from here is not between quantum computers and classical computers. It is between the financial institutions that understood what JPMorgan proved and the ones that did not. The ones who did not understand will be competing with tools that the ones who did will have already left behind.